Hello everyone, I am Professor Ranjit Singh. I am Dean of Affiliations at Shri Vishwakarma Skill University, Palwal, Haryana. I am Chairperson of Industry 4.0 where I am looking the DVOC, BVOC and MVOC program in my university. Today I am here to deliver a talk on logic gates. Logic gates, before studying the logic gates, it must understand what will be the outcome of this course or this content. The candidate will be able to understand the basic knowledge of the digital circuits, digital systems and digital devices. The person will be able to design the digital logics circuits by attending or by looking these courses. Logic gates plays a very important and vital role in digital electronics. Digital electronics is a branch of science, engineering and technology which deals with the design of digital circuits, digital systems and digital devices. The fundamental signals required for all these digital system is normally discrete signal. The discrete signal is normally works on two parts, that is toward the higher value and toward the lower value. The lower value represents the 0, whereas the high value is toward the higher side, that is 1. This kind of representation of discrete signal is normally used in the design of digital circuits, particularly in digital electronics. The 0 means the voltage is very less, that is near to 0.9 volt, and 1 represent in which the voltage is toward the higher side, that is plus 5 volt. In this way, we are going to have the output which will be dependent upon these inputs of 0.9 volt or toward the higher voltage, that is 4 to 5 volt. Now, logic gates are the gates, the circuits which are normally the circuits which represents the output and totally dependent upon the input according to the logical representation of 1 and 0. The fundamental behind this 1 0 is nothing, it is the usually the mode of the logic gate and the input given to these logic gates. There are normally 7 type of the logic gates which are used in the digital circuits or digital systems. The 7 type of the major gates are AND gate, OR gate, AND gate, NOR gate, NAND gate, XOR gate and XNOR gate. This is called exclusive OR gate and exclusive NOR gate. Now, first of all, we are going to discuss the OR gate with this circuit. In this circuits, the two diodes are connected to in a parallel with voltage of VA and VB. The diode 1 is connected with voltage VA and diode 2 is connected with another voltage of VB. We will take the output across a resistance, load resistance, that is RL, as shown in the diagram. Now, first of all, we are giving the input, that is 0, symbolically 0 to both the diodes. When the input will be 0 to both the diodes, under this condition, the diodes will remain off and this output of the whole circuit will be equal to 0, because no diode is working in this condition of both the input equal to 0. Now, we are supplying one voltage of that is 1 at VB. In this case, now diode 2 will be forwarding bias and will be operational and it will be on. Now diode 2 is on while diode 1 is off. Now we will take the output across the resistor, that is RL. The output across this resistor will be 1. Now we applied the third case. Under this case, we are applying a voltage, high voltage, that is 1 at VA and 0 at VB. Under this condition, diode 1 will be active and will remain on, while the diode 2 will remain off. Now we will take the output across the resistors RL. Under this condition, the output will be equal to 1. Now let us see the fourth condition under this circuitry, which is shown here in the diagram. Now we are applying the higher voltage to both the diodes, that is VA is equal to 1 and VB is equal to 1. Under this condition, both diodes will be active and will remain on. Under this condition, the output across the resistor RL and V output will be equal to 1. So in this circuitry, we have seen the four conditions according to the two inputs, because the whole conditions will depend according to the number of inputs supplied to the circuit. In this circuit, we have applied two inputs, that is VA and VB. So number of situations, number of conditions will be equal to 2 raised to power 2, that is 4. Under this condition, we are looking that this circuitry is OR gate, which is the electronic circuit that gives the high voltage whenever there is one input is higher or more than one is higher. In this condition, we have the logic of OR gate which is fulfilled by this circuit. The symbolically representation of this OR gate is like this. In this condition, the Boolean expression of this logic gate will be equal to A plus B. The Boolean expression is the sum of both the inputs applied to that very circuit. Now, the truth table across this OR gate will be according to the all four condition, that is 0, 0, the output is 0. At 0, 1, the output is 1. At 1, 0, the output is 1. And in the last condition, when we have applied the higher voltage to both the inputs, that is 1, 1, we are getting the output equal to 1. Now, let us see the second gate of logic families, that is the AND gate. In this AND gate, the circuit will be designed like this. Now, we have reversed the representation of the diodes. Now, we are applying the voltage toward the N junction of the diode. In this case, we are applying the voltage at A and B, and we will take the output across the LED which is connected across a 470 ohm of resistance, which is very less resistance. Now let us see the operation of AND gate. In this case, we are applying the 0 voltage at A terminal of the diode, and similarly we will apply the same voltage at B point. Now we will see that the voltage, the DC voltage which is across the some resistance, in this condition the both diodes will remain on and the current will exit from the 0 voltage toward the grounded side, and we will have the LED to remain off. the LED will not glow in this condition, and we will have the output is equal to 0. Now, let us see the another condition. In this condition, we are applying 0 voltage at A and 1 higher voltage at B. Now, in this condition, we are looking that the current will flow from the diode 1, and we will have the LED remain off under this condition, and the output will be again 0. Now, let us see the third condition. In this third condition, we are applying the higher voltage, that is usually represented as 1 at A terminal, and less voltage at B terminal, that is 0. Now, under this condition, the whole current will flow from the diode 2, which is connected at B terminal, and the LED will remain off. Under this condition, the output will be again 0. Now, let us see the fourth condition. Under this condition, we are applying the higher voltage at both the terminals, that is A and B. Now, we are looking that current will flow from the LED, and the LED will glow and LED will remain on under this condition, and this will act as a AND gate. And the AND gate is nothing, it electronic circuit that gives the higher voltage at the time when all the inputs are higher at the terminals which we have shown in the circuit diagram. Now, symbolically, we can represent the AND gate like this diagram, and in this diagram we are looking the Boolean expression for this AND gate will be represented as y is equal to A into B, that is the product of A and B. The product of both the inputs will give us the output of this logic gate. The Boolean expression for this AND gate is shown like this. In this, all the four conditions which we have seen in the circuit is fulfilled. Now, let us see the truth table of AND gate. The truth table is represented like this. Now, in this case, we are looking when both the inputs are low, we will have the output is equal to 0. In the second condition, we are looking when one input is high, that is 1, that is second condition where A is equal to 0 and B is equal to 1. Under this condition, again output is 0, as we have seen in the previous case that LED was off. Now, let us see the third condition. In the third condition, we are looking that A is equal to 1 and B is equal to 0. Under this condition, the output of the AND gate will be equal to 0, as we have seen in the circuitry. Now, let us see the fourth condition in which the input is high at both the terminal, that is 1, 1. Under this condition, the output of the circuit or the AND logic will be equal to 1, which has been expressed in this truth table. Now, let us see the third important gate, that is known as NOT gate. NOT gate is the electronic circuit that will produce the inverted version of the input at output terminal. Whatever the input we will apply at input will be inversed at output terminal. It is also called as an inverter. The symbolically representation of NOT gate is shown like this, and the Boolean expression for NOT gate is always represented as like y is equal to A bar. Now, let us see the truth table of NOT gate. In this truth table, we are looking that whenever there is the input, if it is low, the output is high, and if the input is high, the output is low. Now, The third gate is the NOR gate. NOR gate is the electronic circuit which is the combination of two gates, that is the NOT gate and OR gate. This will be connected or designed in such a manner in which OR gate is followed by a NOT gate. The output of all NOR gate are high if all the inputs are low. That is, when we will have the 0 0 input, the output will be equal to 1. The symbol of the OR gate is having a small circuit is represented like a NOR gate. The truth table of NOR gate is shown like this. In this case, we are looking whenever there is the high voltage at any terminal, the output across that circuit will be equal to 0. In this case, we are looking at condition 1, that is 0 0, we are having the output is equal to 1. While in the other case, we are having one high voltage at any terminal, either at A or at B, but we are getting the output Y is equal to 0. Now let us see the another type of the logic gate, that is known as NAND gate. NAND gate is the electronic circuit which is the combination of two gates, that is NOT gate and AND gate. In this gate, the output will be equal to AND gate, which is to be followed by a NOT gate. The output of all NAND gate are high if any of the input are low. The symbol of NAND gate is the symbol of AND gate with a small circuit. The symbolic representation of NAND gate is shown here in this diagram. The truth table of NAND gate is represented like this. In this case, we are looking whenever there is low voltage at any terminal, we will have the output equal to 1. In this case, we are looking that at last condition, the output is 1 at both the terminal, we are getting output is equal to 0. That fulfills the conditions of a NAND gate. Now, here is a very important point, that what are the meaning of universal gate. The universal gates are those gates by which we can design the another three kind of the operation, whether it is the product, whether it is the sum or the inversion. So we call NOR gate and NAND gate as a universal gate. How we can design the all the three operations of AND gate, OR gate and NOT gate by the use of NOR gate, that we will see in this case. If we will merge the input of the NOR gates as a single input, then the output will be equal to NOT gate. Now, if we will club the two NOR gate in this series like this diagram, and the representation of this NOR gate will act like a OR gate. And the third case, when we will use the three NOR gates which are connected in this manner, in this case we will have the NOR gate working as a AND gate. So in this diagram we are looking that NOR gate is giving the operation of inversion, giving the operation of multiplication, giving the operation of summation. So this NOR gate will behave like a universal gate. Similarly, the NAND gate is also known as universal gate. Now in this case also we will have the all three operations can be performed by the arrangement of these NAND gates. If we will arrange the NAND gate in this manner, if we will apply a single input at both the terminal of NAND gate, we will have the inversion, and in this case the NAND gate will act like a NOT gate. Now, the second figure, in this case, if we will arrange the 3 NAND gates in this manner, we will have the output operation is equal to A plus B. In this case, NAND gate is acting like a OR gate because the logical expression is A plus B. Now let us see the third arrangement. If we will arrange the 2 NAND gates in this manner, we will have the output is equal to A into B, and this will act like a AND gate. Under this condition, NAND gate is behaving like a AND gate. So, NOR gate and NAND gate is known as universal gates because of these 3 all operations to be fulfilled by the arrangement of the circuitry of both the gates. Now let us see the exclusive OR gate. The symbolic representation of exclusive OR gate is represented like this, in which we normally represent it within the circle with a plus sign, and the logical expression will be equal to A into B bar plus A bar into B. That is known as exclusive OR gate. And the truth table of exclusive OR gate is shown here. In this case, whenever there will be high voltages or low voltages at both the terminals, then the output will be equal to 0. In this case of exclusive OR gate, when we are applying both the inputs similar at the inputs side, we will have the output is equal to 0. Now we are looking in this truth table that whenever A and B equal to 0, we are getting output is equal to 0. Under fourth condition, whenever there is the similar input, that is 1 at both the terminal, that is at A and B equal to 1, we are getting the output is equal to 0. But in case 2 and 3, we are getting output is equal to 1. So this is the logic of exclusive OR gate. Now let us see the seventh important gate, that is exclusive NOR gate. We also call it as XNOR gate. In this case, the symbolic representation of this logic gate is like this, and the Boolean expression is given as the product of both the inputs, that is A into B, plus inversion of both the inputs, that is A bar and B bar. The logical expression of exclusive NOR gate is given as A into B plus A bar into B bar, and we can also represent it like a dot within the circle, and that is A dot in the circle into B. The truth table for exclusive NOR gate is like this. Under this condition, we are looking that whenever there is same input available at both the terminals, the output will be high. Now, in this case 1 at case 4, we are getting output is equal to 1 because the input is same at both the terminals. While in the case 2 and case 3, we are looking that the input is not same, input is not identical, and we are getting output is equal to 0 at case 2 and case 3. So this is all about the 7 type of the logic gates by which we can design any kind of the digital circuit or the digital device which will be helpful for the digitization of any important documents. Thank you very much. Thank you.